Hi everybody, so thanks for tuning in. This is part of a series of videos where we're going to be meeting with the subsection leads from the Western Formula Racing team, discussing a little bit about the build of the WFR19E. So today here we have with us Aidan McLeod and Luke Grigoris. Thanks for joining us, guys. They are from the gearbox team, so we're going to chat with them a little bit about our gearbox design. So first for you, Aidan, can you quickly walk us through the design cycle of the gearbox for this year?
Yeah, so because we'd never designed a gearbox before, as a team, we've since this is the first year that we're electric, we needed to use a ground up approach, obviously, because we had never done this kind of thing before. So we started with final drive selection. So that was a big thing because we needed to select the appropriate final drive based on our motor capabilities and to get the kind of torque curves and the performance we wanted. So we started with that using some simulations. Once we identified the final drive that we wanted, we began a sort of an iterative design process to outline the sort of the high-level parameters of the gearbox, so the center-to-center distance, the number of teeth per gear, that kind of thing, and sort of like the high-level type design. Once that was finalized, we actually went to met with a gear expert from McLaren Engineering, had a initial design review, so he took a look at what we had so far, let us know if or gave us some suggestions, let us know what was going to work, what wasn't going to work, so that was hugely beneficial. And then from there we started in-depth design, so we started doing simulations on KISS soft, hand calculations, FEA analysis, that kind of stuff, sort of to validate our designs and make sure we were getting the factors of safety we wanted and to make sure things were going to hold up for several seasons, because that was one of our design goals. And then once we had all the gears and shafts finalized, we began out with the housing design. So the gearbox housing itself, we began design of that, the seals, the housing itself, making sure it's nice. It was as stiff as possible, and it would be able to handle the loads going through it. So that housing was sort of the last thing that we finalized, and that was sort of marked the end of our design.
Cool. So Luke, can you take us a little bit through about like how did your initial design methodology differ from last year?
Well, in previous years we were running a sprocket chain driveline, and this year was completely, as Aidan was saying, a complete ground up approach. And since we looked at an analysis of sprocket chain and we saw that it wouldn't quite fit with the full monocoque that we were trying to do this year, and so we decided on doing a gear drive that would not only find the final drive that we were looking for as in a tight package, but as well give the team a knowledge on gearing and gear design and proper gearbox design for the later years. And also another change is the fact that we used an electric motor. This was very different this year, so we had to completely rethink our final drive selection based off the peak and continuous torque values. So that was pretty difficult this year as well. But yeah, I think that's pretty much it.
Do you think so, Aidan? What would you say was the main challenge in designing and building the gearbox this year?
So packaging was definitely our biggest concern. So with our new full monocoque design, the rear packaging, where the motor, the accumulator, the gearbox, all the drivetrain components, cooling components, everything's back there in this small little space. So we had a very tight constraint on center to center distance, and we had a very tight constraint on making sure our tripod bearings were within a certain angle, right? Because for our drive shafts, so that was a really big constraint, and it was very tough to make sure that we were fitting everything in, and what the decisions we were making, the design decisions, the packaging decisions, were aligned with what everyone else was doing, working sort of in the same area of the car. Yeah. So that was definitely a huge challenge. It took a lot of time, a lot of collaboration with the other subsystems on our team. And then the other challenge we had was sealing. The sealing of the gearbox was, we wanted it to be robust, reusable, and reliable. So that was another thing that we put a lot of time and effort into, is figuring out how to seal it so we wouldn't have any problems.
Cool. So I think, Luke, you alluded to something earlier about the major change in the team's methodology of the EV. So what are some of the specific challenges related to the switch to EV that the team was presented with?
Yeah, like as I mentioned earlier, the final drive was the most difficult, I think, just because we had to run through so many in-depth simulations because of the motor's tendency to go for peak and continuous torque. It's a lot more versatile, but in peak torque, the motor overheats like way more readily, and it will reach a temperature that is no longer in its operating range, and we might actually permanently damage the motor. So we designed for more of a continuous torque value, which it lets us cool the motor at a rate where it will no longer heat up. So our final drive is designed for the continuous torque region, and in this way we can still more aggressively. We still have to aggressively gear the motor, but we don't lose as much high-end top speed because of the high RPM of the MRAX 228. So we can still achieve a performance without hindering the motor's structural integrity. But with that being said, with this more aggressive gearing, we get more overall torque to the wheels if we ever do get into that peak torque region, which gives us overall faster acceleration off the line.
Gotcha. Okay. So, what type of gear train did you guys end up choosing for the driveline? Like, why that specific configuration?
So our decision was based mostly off of packaging. As I said before, that was a huge concern for us. So we chose a double reduction spur gear design. So 4 gears, 2 reductions. Double reduction because you can fit a bigger reduction in a smaller space. As I said, we had a really small volume constraint, so we managed to jam a large reduction into a small space given that design. And then we use spur gears just because they're efficient, they're easy to manufacture, and it avoids having to design for, because if you use like a helical gear, you end up with axial loads on the shaft. So there's more consideration based in the design and the bearing selection, that kind of thing, that we were able to completely eliminate just by going with a basic spur gear design. And spur gears are often avoided mostly because they're loud, but noise isn't really a concern for us. So we chose to pursue that method. So that was sort of our methodology for choosing the high level gear train design.
So we're back here with Dave and Luke, and we've covered a lot of the design process, so we're going to just talk a little bit about manufacturing. So Luke, do you want to take us through a little bit of the manufacturing process for the gears this year?
Yeah, for sure. So our gears this year were manufactured by Linamar, who's our sponsor. Here's one of the green gears, they call them, which means that they're unheat treated. So the first thing they did was just machine the overall blank profile, which is just the outer diameter and then the inner diameter with these weight saving pockets and these holes. And then they would proceed to manufacture these splines by a wire EDM. And then they would cut the teeth on a hobbing machine, they call them. And then after that, they would take their take CMMs and other quality and analytics machines, and they would just trace over these profiles and make sure that they are all to spec, and as well gather this data for after heat treating to make sure that they didn't distort too much from the high heat. And so here's an example of a heat treated gear that was out of spec. So they basically use a carburizing flame or a gas carburizing flame, and they create a hardened profile on the outside so the teeth can take much more contact stress. And so that's how these are manufactured. And then they would also analyze these again to make sure that they didn't distort over the heat treating process.
So what about the rest of the components of the gearbox, like the housing and all of that? Can you chat a little bit about how that went?
Well, the shafts were manufactured in a similar way to the gears. They were turned on a CNC lathe, and then they were cut with the external splines that we showed there. And then they were heat treated in a similar fashion. Whereas the housing was manufactured by Bryac Machining, and it was a CNC aluminum housing in 2 pieces, and it's made of 7075, which is like a high grade aircraft grade material that has a very high tensile strength.
Okay, and then finally, can you just walk us through, what's the driveline going to look like for next year? Kind of what is your guys' vision to pass on to the future teams?
Yeah, so we set out with one of our goals was we wanted this gearbox to be usable for several years in the future to sort of allow other areas of the car to get developed in case no changes are made to the drivetrain in the next couple of years. But ideally, so the next step in the process would be the idea would be, right now we run 1 motor that feeds the whole rear axle, but the next step would be run 2 motors in the rear for the feeding that same axle. Which would require obviously another gearbox. And then after that, the next step would be sort of like the final step would be running in-hub motors in all 4 wheels, which would require probably planetary gear sets. And so that would be another development in the gearbox life cycle of the team, would be getting to the stage where we have planetary gearboxes in all 4 wheels. which allows for a lot of really cool and interesting sort of traction control systems and that kind of thing. And having four-wheel drive is a huge benefit as well. So that's sort of the holy grail for drivetrain.
Yeah.
Now that we're electric, so it's we're looking forward to seeing what the team's going to be able to do in the future.
Absolutely. Well, it sounds like you guys have set up pretty well for success. There's been a lot of good developments this year. So, thanks, guys. Really appreciate your time. Aiden and Luke, guys, thanks for tuning in, and we'll see you next time. Hi everyone, so we're back with the next series of our videos for the 2019 season, just highlighting some of the subsections for the WFR 19E. Today we're going to Graham Dishman, who's the subsection lead for our chassis. Thanks for coming on, Graham. Really appreciate it.
Good to see you, Alex. Thank you.
So yeah, this was a big undertaking for this year. The first time we've had a full monocoque for the team. Why did you choose this year particularly to attempt the first?
So there was a lot of reasons. I think first and foremost was kind of that we wanted to kind of take on a real challenge and learn as much as we possibly could. But then also we were kind of following the logical progression of the chassis. So 2015 we had our first monocoque. 2017 we removed some of the steel tube frame in the rear, replaced it with composite materials. And of course this year we replaced the entire steel tube subframe for the full monocoque, completing the design timeline, I suppose. We had a lot of composite experience, including about 10 years of cumulative chassis experience, including myself and two other ex-leads. So a lot of experience to draw on. And then of course, switching to EV got rid of a lot of the hurdles that we were kind of coming across when we were thinking about going with the full monocoque.
Good. Well, it sounds like you have good undertaking and good timely, with the EV transition.
Perfect timing.
Okay, then so kind of what was your main focus in designing and building the chassis this year in terms of integration, weight, and things like that?
So emphasis always on safety, maximizing safety and minimizing mass, of course. But then also this year we had a great opportunity to kind of look a lot at integration. And that came mostly from the fact that we're doing a full redesign from the ground up, essentially. And just allowed us to kind of look at previous years and draw on our experience and kind of make sure that the integration for this car was the best the team has ever seen, essentially. Yeah.
And obviously this was a challenging undertaking, like you said, this is the first time we're doing this. So what are some of the challenges, both anticipated and not, that the chassis team was presented with this year?
So the timeline for the full monocoque was something that we had anticipated, but me myself, I didn't really respect how difficult it would be to kind of complete some of these goals while I was balancing a full course load. So just designing brand new geometry, integrating the new EV powertrain, brand new set of molds to design a rapid schedule. Just that with exams and assignments, of course, it was just a daunting task. So luckily made it through. And then also making sure that we had all of our rules knowledge of the stuff and that we could give it close attention to everything and then make it through our technical inspection with a safe and competitive vehicle.
Yeah, I guess that's the thing at the end of the day, right, is to make sure that it's not only fast, but that it abides by the rules. So what do you think for this year makes this monocoque special? Like, what's going to make it stand out with the other teams?
So I guess at a first glance, the first thing that you see is that we're running a full planar design, which is something that not a lot of teams do. Typically they'll pull on certain elements, but we're one of the few teams that kind of goes full monocoque, that's planar. And that kind of extends the rest of the aesthetic of the car. A lot of other subsystems will kind of draw them into the car, and once they're mounted, it really does kind of pull everything together and it looks very clean. Another thing that not a lot of teams are doing as well is that we're dropping our accumulator through the floor. And so our rationale for that was that we don't want to put any of our members in a situation where they might have to awkwardly lift a really heavy pack through the firewall, or the design challenges that would come with a full monocoque and removing it through a rear plane.
Right.
So we actually integrated that into our accumulator cart, and so we actually installed a jack that would come up towards the accumulator and then lower it down with a mechanical advantage. So at no point between dropping it from the car and moving it to a battery charging station, at no point does anybody have to lift the pack.
That's certainly a convenient design, right? You always think about the servicing, not just the manufacturing and the design stage for sure. Hi everybody, so we're back here with Grant, still talking about the chassis for the WFR 19E. So, Grant, you talked a little bit earlier about the need for integration of the chassis with the new EV system. So, what are some of the areas that highlight the integration with the rest of the vehicle and the other subsystems?
There's a lot of things, but some of my favorites, I'd probably say that the swept rear frame that kind of accommodates the proper angle for our diffuser and our under tray was definitely a good one that we kind of worked on from day one with the aero lead. And I'm really glad that made it onto the car. The front suspension, having everything on one plane, definitely reduced the complexity of the kinematics that they were having to deal with, and definitely gave them a little bit more room for iteration in future years. We have a very narrow cross section, which allows us to have a very narrow track width, which is very beneficial. And then, of course, we have a lot of pocketing in our core throughout the monocoque, which allows us to kind of maximize the amount of space that we have for packaging, and then also drop our CG in a couple places, like we're able to drop the driver a full inch to the lowest point of the car, which actually is quite a considerable amount in CG.
Yeah, I guess chassis implicitly is one of those systems that has to integrate with every other subsystem because everything's basically housed in the car. So I'm sure it was really great. So what would you say, kind of to sum everything up? What would you say you're most proud of on the chassis design and the manufacturing process for this season?
Honestly, this year, I'd say the thing that I'm most proud of was just the commitment from the entire team to make sure that we had a full monocoque at the end of the build season. I couldn't be more impressed, honestly. I found myself pulling a lot of late nights next to other subsystem leads, really committed members, and some really fantastic recruits. I could not have done it without them. Honestly, I just really like to thank them for all their support and their generosity with their time. And I'm just so excited to see the monocoque compete at Formula North in Lincoln this year.
Yeah, I think everyone's going to be excited. We're all excited as well, and hopefully you'll join us there with Grant Leishman. So thanks for joining us, Grant. Really appreciate it. Thanks for your time, and tune in for the next one, guys. See you soon. Hi everybody, so we're back here on our series of videos for the 2019 season with the Western Formula Racing team. We're talking to a few of the subsection team leaders about their subsections and how they're contributing to the WFR season. We've got Alex Brony and Ian Stother with us from the electrical team. So thanks guys for joining us today, really appreciate it. So I guess let's start with the high-level picture. How would you describe design methodology and the focus for this year?
I guess for this year on the switch to EV, we mainly wanted to focus on making a vehicle that was simple, that had components that all integrated with each other very well, and wanted to be very robust and high performing. So, to give you an example of simplicity, we could have chose to do a traction control system that was based off state-space logic, but we went with a more conventional that's tried and true and should perform well. For an example of integration, we chose our motor inverter EMS system that integrated with each other, as well as our chargers that all integrated well with each other out of the box. So that we knew that we'd be successful going into the future. And in terms of robustness, we have backup systems, fail-safes, for the control logic of our vehicle to ensure that in the event of a traction system failure, if, say, a wheel speed goes out, we have a fail-safe in place to just go into direct torque drive mode for the as opposed to stopping.
So obviously a lot of work's gone into the design process and a lot of thought put into that. So what, Ian, if you could take us through, what are some of the performance benefits you hope the team will achieve with the new EV powertrain strategy over kind of our ICE approach?
Yeah, so one of the nice things is that since we have so much control over how the car thinks with the controller, we can tune these specific vehicles. So we can estimate what kind of slip the car will be going through based off of our traction profile. We can also integrate on the drivers to tune the vehicle response to the vehicle. So we can tune the snap response, we can tune the accelerator pedal response to them. And we can essentially look at anything the car can see, we can integrate that into how the car behaves. So we can account all sorts of factors on how the car performs.
So we're back here with Ian and Alex, still chatting about the EV powertrain. Tell me, Alex, what are the main factors that are most unique about the system that you designed for this year?
I guess I'd say the most unique component of our vehicle.
It's currently connected to this one.
Our vehicle control. And using the motion M150. In our previous year of competition, we got the low-tech as an engine controller for our vehicle. And what we found with it is that with the development license and the controller, we're able to completely rewrite the firmware for the device. And with that, what we were able to do actually is completely gut out all the internal combustion engine code and rewrite the firmware for the electric vehicle.
Yeah.
This allowed us to have cost savings and probably as far as I know, only one other team in Northern SAE team has been able to rewrite the firmware for that for them in the past. Now, in terms of other things that we're doing at team, we have, for the first time this year, wireless telemetry over Wi-Fi, and where that's connecting is through the serial on our Reinhardt. We have that on Wi-Fi, as well as direct connection to our low-tech controller. And through that, actually, because all of the devices on our car, or over 7 devices on our car, are connected to communication, we're able to get live telemetry data on almost every system on our vehicle, including the battery management system, information that we get to our dashboard, and specific communication between the ECU and the Reinhardt.
So, a big principle in integrating those systems for,
That's the biggest hood scoop ever fitted to a production car.
Yeah, tell me what if anything, is going to be important in terms of manufacturing parts or service, because obviously that's a large part of it.
Yeah, absolutely. So one of the biggest challenges we had this year was the sheer amount of components we ordered. So if you look at the electrical system in the previous year, maybe it were between 20 to 30 components. This year we ordered around 2,000 unique components. So just tracking all of that and centralizing the tracking of that. And then also one of the other things we did in addition to centralizing the tracking was we implemented a lot of tools that are just free tools such as Octopart. And we were able to take one part number, punch it into a database, and then locate the cheapest source for that part. And so one of the things we did to keep costs down in terms of shipping was we amalgamated all our parts into and so that kind of cut down on shipping, and then also just made it easy.
That box is fried.
So that's one of the biggest differences in terms of quality. In terms of manufacturing, obviously,
has
a lot of new systems like new custom circuit boards. What we found is people just because circuit boards are very interesting design, and it's almost like programming a physical thing. So from a physical programming it's good to get the boards together, solder it together, test it, and make sure it works. Identify what the issues are, and then your next board should be perfect.
Small and delicate compared to the other two, but no doubt.
What do you think, Alex, has been the biggest challenge?
perfect. Can you put it on that table there?
As in terms of challenges for 2019, the biggest would be dealing with the whole problem of the accumulator. Now, with being the first electrical vehicle and dealing with a 400 volt battery, that can be like daunting.
Yeah, no, I think that's
from
right.
a safety perspective and getting yourself educated.
Yeah,
on
so
how
let's
to deal
rip
with
up
that, and in terms of a sourcing and fusing perspective. Now, for sourcing, we had to go through many different cells to find cells that at the voltage we wanted allowed for an efficient energy density as well as power density, and not only that, fit in the package that into your packaging. Now, after all that was dealt with, we still had the fusing problem. Now, as a first-time team, it's hard to develop a fusing methodology on top of all the other tasks we have to do for an EV. They're testing fusing and actually getting the equipment in-house to reliably fuse every single cell and ensure that we're not having failures at competition. What we ended up doing was going with pre-built energy cells that do the cell balancing and fusing for you. So you just have to connect to the bus and that helped take a little bit of the focus off of that challenge and allow us to focus more of our time and effort on the traction control system.
So it was obviously a very large change from last year and a huge development push, but very complex system
That's
in
okay.
itself. So why
Why don't we
choose
figure
a
out
single motor?
what's
What
going
was the
on?
reason behind that?
Yeah.
Yeah, so one of the main
Did it
issues
unplug
when you're
from over
building
there?
a new system
Oh,
is
can you
that,
plug back in?
as you mentioned before, I want to keep it simple. So, in an effort to keep it simple, we source a lot of parts that are manufactured, so our drives off the shelf, our motors off the shelf, even our battery pack for the most part is off the shelf components integrated together. And so when you look at the available motor drives on the market right now, most of them are geared towards either consumer cars or larger vehicles that you're building. So if you're gonna build a drive for a dual motor system, you would need to build your own inverter in terms of like to make sense logically. So our drives fairly well in terms of other drives in power class, but there's not many inverters available at lower power classes. There's not many inverters available at and then in addition to that, a lot of these companies immediately start with 2 or 4 motors. There's a lot of problems technically with that. It's more complicated. There's a lot more programming involved. So it's much easier to transition from a internal combustion engine straight to a single motor because we're plugging into our old differential through the new gearbox. And testing can be done on the old dyno we used to use. So it just made a lot of sense in terms of how complex it was going to be, and then just dealing with all the other moving parts. So integrating all the small systems I was talking about earlier, and making sure everything's going to work well for the car.
Sure. So again, I think going back to our team, philosophy of the season, kind of simplicity, integration, performance, kind of all in one package, not jumping too far ahead in the development stage.
Absolutely.
I think is hopefully going to help us out throughout the season. So why specifically the 400 volts system? Why did you go with that?
I guess that's a loaded question, in that it was a big team integration was required to choose that system voltage. And the reason being for that is you'll find when creating an accumulator, dependent on the package that you have to work with in terms of sizing and physical layout, you have to deal with the different types of cells you want to use, pouch versus cylindrical, the type of cylindrical. And with that, you can have different layouts of those cells, and with those different layouts and different voltage levels, you'll see that there's a trade-off between the voltage level you're running at, the power density you have, and the energy capacity that you can have. And we found for the 18650, or for very popular 18650 cells, the 400 voltage range for our package made a lot of sense in terms of the energy capacity that we were looking for. And we found that, I guess, through a set of course data in terms of simulations running down through endurances, and to see exactly how much energy we think we would consume through the course of an endurance. So we had a target for the energy capacity that we wanted, and we had, with that, we could plug for the other 2 things, the voltage that we needed and the power output we needed from our pack. Okay. And with that, it was a effort to work with more of our actual traction selection in terms of motor and drive to see what worked well at different voltages. I guess, do you want to speak more about that, Ian?
Yeah, absolutely. So in terms of how I selected voltage, I really didn't think about it until the very end. So I picked a whole bunch of motors that would work for the car, and identified what voltage range they would operate at, and then I found drives that would pair with those motors well. And so based upon that, I had a whole bunch of different combinations between electric motors and electric motor drives. And so I went to Alex with a whole bunch of different options, saying, hey, we can run at 400 volts, we can run at 600 volts, we can run at 200 volts. Here's what it looks like in terms of our powertrain's weight. And so based off that, Alex's goals and my goals, and just trying to keep the vehicle weight down and maximize our power density, we ended up at 400 volts in the end.
Makes sense. So again, it's like everything else, right? A team effort of integrating all those decisions. So obviously a big change from last year to this year. Where do you guys see the EV powertrain evolving for future years for the team?
Okay, I guess I can start with that. So in terms of what I think the biggest change, or the most necessary change needed in the future is to get rid of the energy cells that are in our package. Unfortunately, Energis doesn't allow you to pick custom fusing for your cell modules, so we're stuck at each cell being fused at 20 amps each, even though those cells specifically can be fused to 30 amps. Now, in addition to that, the fusing data isn't as great from those Energis cells as well. So I think in terms of getting costs down on the accumulator pack and having that in-house capability to build internal cell modules where you can measure the temperature and voltage easily off those cells, I think would be the biggest performance gain for our team. We can almost instantly, with a lot of with the same package, get a lot more performance for much cheaper. And it's just that in-house knowledge needed on fusing to get there.
Then I guess from my end, once the accumulator is sorted out, which is definitely the lowest hanging fruit in terms of performance gains, then the team could look at getting a bit fancier with the actual external powertrain setup. So I'd probably start at the inverter. So there's no inverters or there's not many inverters on the market that make sense in terms of weight if you're going to run 2 motors. So the first thing I would do is develop our own inverter, our own dual inverter with pre-purchased motors for a dual motor system. And then after that, you could look at doing a quad inverter or getting fancier than that and running a 4-motor system. And then once your inverter is really ironed out, you've kind of maxed out that capability in terms of improving the performance of your vehicle. And then the last marginal gain there would be finally to integrate with the uprates with the motors somehow. So we've talked about a whole bunch of crazy different ideas, like having a static outer motor casing that was the upright, or just having a motor that plugs right into the upright. The performance gains are very small compared to what we can gain in the accumulator or making our own inverter, but that would be maybe 10, 15 years out, which sounds really cool to see on the car.
Nice. Well, thanks, guys. Alex and Ian, no strangers to challenges and innovation. Obviously, looking forward for the team and making a huge development leap. So, thank you for joining us. Thank you, guys. Appreciate your time, and we'll catch you guys again next time. Thanks very much. See you soon. Hi, everyone. Thanks for joining us again. We're back here with our subsection speaker series. Today, we've got Ben from Aerodynamics. We'll be chatting a little bit with Ben about our development of the aerodynamic system this year for the WFR 19E. So, Ben, just to start out, do you want to just take us through kind of the design philosophy this year for the team's aerodynamic components?
Yeah, so this year we really we just wanted to make sure that aero was actually beneficial to an EV car, since we've never gone EV before. So we just kind of wanted to really start off with the biggest questions. Obviously, first being, is aero worth it? So we kind of just started doing lap time simulations, figuring out, you know, is downforce good, and well, we know downforce is good, but is the drag still worth it? And then obviously the weight, we have to accelerate more mass, we have to put in more batteries. Ultimately, we determined through simulations that aero is totally worth it. It has a little bit more of a penalty on than a combustion car because of the increased energy density of lithium ions over gasoline. But overall, should still work. Ultimately, we're going to test that while we have the car built. But yeah.
So how would you say largely that this differed from the design methodology, let's say, if we were to go with internal combustion car this year?
So I guess the biggest thing is with combustion car, it was really, in order to maximize performance, it was mostly just maximize downforce. And like the drag penalty didn't really matter because like we didn't really care about efficiency as much, just because like there wasn't as big of a mass penalty.
Right.
Whereas with EV, you have to put in more weight into the battery pack. I believe this year we added like an extra 0.8 kilowatt hours to the battery pack, which it worked out to be something like 4 or 5 kilos. But yeah, like I was saying before, it should actually be beneficial to the car.
So I guess so with that change in methodology in mind, what are some of the major design changes in the aero components that you came to through the design phase?
Okay, so one of the big things early on that we decided what we wanted was to implement an under tray for the vehicle.
Mm-hmm.
So we kind of did some research and found that under trays tend to obviously create more downforce, but have a very minimal drag penalty. So that was pretty much ideal for the electric powertrain. Like I was saying, we don't have to put in more batteries.
Mm-hmm.
We also made some edits to the rear wing. Ultimately, we vastly improved the lift to drag ratio in the rear wing. And then because competition has the Endurance, Autocross,
Mm-hmm.
and Excel, we made both front and rear wing adjustable. So
Mm-hmm.
for Excel, as a good example, we're just gonna, have a very low drag configuration, as the downforce isn't really critical because it's just straight line speed.
Yeah.
And we changed the front of the car dramatically so that the under tray was actually effective. Previous years were doing research and found that the previous configuration of the front of the car actually choked off a ton of under the vehicle
Really? Okay.
airflow. So
Yeah.
we have a higher nose
Mhm.
and a massively different front wing. It's actually pretty cool.
So a lot of, obviously the under tray drove a lot of other development changes up front of the car because you're trying to manage the airflow all the way from the back to the front, right? So it's kind of driving a lot of your decisions on what to do on the front and the back end as well.
Yeah, well, we knew that we needed air to get underneath the car.
Right.
So, like I said, having the higher nose, the front wing has a gap between the nose cone and the trailing edge of the front wing, so
Yeah.
that air can actually go underneath.
Yeah.
What else?
Talk a little bit about what were the kind of specifically, the under tray is a big project for you, of course. So what specifically in just the design of the under tray, what were your considerations there in terms of the design and the manufacturing specifically? What were kind of some of the things you wanted to
Okay,
consider?
so, we kind of knew what we needed to hit in order for the under tray to actually be beneficial
Mhm.
to the car. I can't remember the numbers off the top of my head, but
Mhm.
there was a certain lift to drag that we had to hit. There's a certain mass to downforce ratio where if we were below,
Mhm.
it would have actually just made the car worse.
Right.
So obviously we had to make sure that we were still
Mhm.
improving the car, and then with benefits to make all the additional effort worth it.
Mhm.
So yeah, that's what we were really aiming for with the under tray. And then in terms of manufacturability, we knew we wanted to use composites. Personally, myself, I have a lot of experience with that, and I know the team is very well versed in it now. So we were pretty comfortable with designing composite part, and then working with MDF, the monocoque molds, and
Mhm.
pretty much every single composite tool. I shouldn't say composite tool, but any tools for composites
Mhm.
are mostly MDF on the team. So
Yeah.
we were pretty comfortable with that, and then it was just really making sure that we could get tools into the radiuses and stuff like that,
Mhm.
so that it was actually manufacturable. There were a couple concepts that were made at the beginning of the year which were not manufacturable.
Yeah, yeah.
And we had to iterate a little bit.
Sure, yeah.
So, yeah.
Kind of building on the integration piece that you just talked about, obviously with this whole change, especially the under tray and building in all the tolerances and access to tools and all that, how does this new aerodynamic layout affect the other subsystems? So what are some of the considerations, I guess, that you had to work with the other subsection leads to ensure that this can all come together in the end?
Yeah, that's a really good question, because one of our team goals one of our car goals this year was integration. So making sure that the whole car works together and that subsystems are communicating properly. So very early on in the car design, we realized that we wanted to have the battery become detachable
Mhm.
from the bottom of the car.
Right.
So we saw at other competitions, the other EV teams were lifting like these 100 pounds battery packs out of their car, and it just looked painful. So early on, we decided we wanted to drop right out, and we wanted to have our own accumulator lift.
Yeah.
So obviously the under tray is a barrier to that. So in order to make the team's life easier, we put in special considerations to the under tray to make it easily detachable. So there's like 6 fasteners. We only need to have access to a nut on the under tray, so we can just get under with a tool and just rip them off and then remove it. So yeah, we wanted that to be quick and easy. The under tray is integrated with the monocoque pretty tightly, especially in the rear. We realized we didn't want the diffuser section to just hang off the end of the car. So if you look at the monocoque, there's like a cutaway, and it's parallel to the diffuser angle. That was just so exactly like it doesn't overhang a lot. I'm just thinking about it now. The jack bar was actually designed by the Aero subsystem because we realized that if we wanted to lift the car with the tires on, for example, we couldn't just put a stand underneath the under tray as probably damage it. So we designed the jack bar so that it was actually, we could put our jack stand underneath of it and like remove the tires that way. We'd seen other teams where they'd put the car on tire stands and then they'd remove the under tray and then put stands on to remove the wheels. So like many processes just to remove the tires, and we're like, okay, we don't want to do this. Like, so
again, the simplicity, integration, performance kind of philosophy.
Yeah, exactly.
Yeah.
So I think that's a good example of good integration. I can think of another one right now. The rear wing. Last year we had all these struts that held up the main element of the wing, and it was a barrier to access in the rear of the car. And pretty much everything is in the rear of our car this year. So that was one of the motivations to move to swan neck mounts. So obviously a downforce improvement as well, and it looks pretty cool. But I guess that's a good integration piece.
Yeah, and that's something when we had Grant here from the chassis team. That's something that they described again is having those the ease of access to the accumulator and making sure that we make it easy for the team to work on the car as part of that. So what do you think? Obviously, this is a lot of major changes that you just took us through that we did for this year. What do you think what was the main challenge that you had this year that you had to tackle, and maybe a couple ones that maybe planned for or anticipated or didn't anticipate? But what was kind of the main one?
I don't know if I can nail it down to one issue. Okay. I'd say, like, big picture, the biggest issue was the pace at which we had to make design changes. Like, here's an example. Like in September, I think it was in the beginning of September, the team made a decision that we were gonna stick to our 9-inch Hoosier wheels, where we were discussing using a different tire, and that had pretty big effects on Aero because the keep out zones were different, and it had a large effect on the under tray. And like I was talking about earlier, where there was like a specific downforce to drag ratio that we wanted to hit, and mass. When we changed tires dramatically, everything changed hugely because of something that we weren't really familiar with because it's our first under tray. But so that was like a challenge that we kind of worked through. The monocoque changes had some effects on like how big the front wing could be. And like, Aero had to be done really quickly because suspension's kind of built off the Aero sensitivity. So I'd say the biggest thing is the rate at which designs had to be changed, and really now we're finished the manufacturing process. But
so I guess with these drastic changes and the evolution that we've had over the past few years, but the big step change in this year. Where do you see the team going in the future with aerodynamics? So like, what would be, if you were going to be around for the next few years, what would you like to see developed on the car? Is there something specific?
Yeah, well, I think the team can take aero in like a number of, I don't know, different avenues, but there's multiple projects that should be done to improve the car further. So something that comes to mind now is DRS. Like the team has always talked about it. And in 2015, they had a functional DRS system.
Right.
For EV, it would have an advantage where we can run a more aggressive aero package for endurance.
Okay.
So we can get higher turning, lateral accelerations and stuff like that. But on the straights, when you're going fast, you're not getting that drag penalty because and you don't need the extra grip really when you're going straight.
Sure, yeah.
So DRS would be good there because we could reduce the battery size. I know the front wing can definitely be stronger. DRS stands for drag reduction system. Like it's F1 cars have it essentially like the rear wing opens up a little bit, so they get less downforce, but also less drag, so they can overtake other cars on the straights. But for us, like I said, it would just be to reduce the battery size. The front wing could be definitely built up a little bit more. We're not fully taking advantage of the keep out zones regulated by the rules, and that's just to keep it simple this year because I wanted to mitigate some amount of risk.
Yeah.
But that could definitely be further improved. The under tray is like pretty low on the diminishing returns, I'd say currently.
Okay.
Yeah. Like I was saying, we had to go through many fast iterations. That doesn't mean we put in a huge amount of iterations. Like there's probably quite a bit more potential there.
Yeah. Well, it sounds like there's kind of a lot of, we've given the team a good foundation for the future. There's obviously always incremental improvements to have, but I think we've had a good year, and it's definitely going to be. It sounds anyway like the aero is definitely going to be a major part of our winning strategy for the year. So really appreciate your time, Ben Cogswell from the aerodynamics team. I really appreciate him coming out, and thanks guys. This is going to be the last one of these series, and we look forward to seeing you out on race day. Thanks very much for joining us. Hi everybody, so thanks for tuning in. This is part of a series of videos where we're going to be meeting with the subsection leads from the Western Formula Racing team, discussing a little bit about the build of the WFR 19E. So today here we have with us Aiden McLeod and Luke Grigoris. Thanks for joining us, guys. They are from the gearbox team, so we're going to chat with them a little bit about our gearbox design. So first for you, Aiden, can you quickly walk us through the design cycle of the gearbox for this year?
Yeah, so because we've never designed a gearbox before, as a team, we've since this is the first year that we're electric, we needed to use a ground up approach, obviously, because we had never done this kind of thing before. So we started with final drive selection. So that was a big thing because we needed to select the appropriate final drive based on our motor capabilities and to get the kind of torque curves and the performance we wanted. So we started with that using some simulations. Once we identified the final drive that we wanted, we began a sort of an iterative design process to outline the sort of the high-level parameters of the gearbox, so the center-to-center distance, the number of teeth per gear, that kind of thing, and sort of like the high-level type design. Once that was finalized, we actually went to met with a gear expert from McLaren Engineering, had a initial design review, so he took a look at what we had so far, let us know if, or gave us some suggestions, let us know what was going to work, what wasn't going to work, so that was hugely beneficial. And then from there we started in-depth design, so we started doing simulations on KISS soft, hand calculations, FEA analysis, that kind of stuff, sort of to validate our designs and make sure we were getting the factors of safety we wanted and to make sure that things were going to hold up for several seasons, because that was one of our design goals. And then once we had all the gears and shafts finalized, we began out with the housing design. So the gearbox housing itself, we began design of that, the seals, the housing itself, making sure it's nice. It was as stiff as possible, and it would be able to handle the loads going through it. So that housing was sort of the last thing that we finalized, and that was sort of marked the end of our design.
Cool. So Luke, can you take us a little bit through about like how did your initial design methodology differ from last year?
Well, in previous years we were running a sprocket chain driveline, and this year was completely, as Aiden was saying, a complete ground up approach. And since we looked at an announced sprocket chain and we saw that it wouldn't quite fit with the full monocoque that we were trying to do this year, and so we decided on doing a gear drive that would not only find the final drive that we were looking for as in a tight package, but as well give the team a knowledge on gearing and gear design and proper gearbox design for the later years. And the big, also another change is the fact that we used an electric motor. This was very different this year, so we had to completely rethink our final drive selection based off the peak and continuous torque values. So that was pretty difficult this year as well. But yeah, I think that's pretty much it.
Do you think so, Aiden? What would you say was the main challenge in designing and building the gearbox this year?
So packaging was definitely our biggest concern. So with our new full monocoque design, the rear packaging, where the motor, the accumulator, the gearbox, all the drivetrain components, cooling components, everything's back there in this small little space. So we had a very tight constraint on center to center distance, and we had a very tight constraint on making sure our tripod bearings were within a certain angle, right? Because for our drive shafts, so that was a really big constraint, and it was very tough to make sure that we were fitting everything in, and what the decisions we were making, the design decisions, the packaging decisions, were aligned with what everyone else was doing, working sort of in the same area of the car. Yeah. So that was definitely a huge challenge. It took a lot of time, a lot of collaboration with the other subsystems on our team. And then the other challenge we had was sealing. The sealing of the gearbox was, we wanted it to be robust, reusable, and reliable. So that was another thing that we put a lot of time and effort into, is figuring out how to seal it so we wouldn't have any problems.
Cool. So I think, Luke, you alluded to something earlier about the major change in the team's methodology of the EV. So what are some of the specific challenges related to the switch to EV that the team was presented with?
Yeah, like as I mentioned earlier, the final drive was the most difficult, I think, just because we had to run through so many in-depth simulations because of the motor's tendency to go for peak and continuous torque. It's a lot more versatile, but in peak torque, the motor overheats like way more readily, and it will reach a temperature that is no longer in its operating range, and we might actually permanently damage the motor. So we designed for more of a continuous torque value, which it lets us cool the motor at a rate where it will no longer heat up. So our final drive is designed for the continuous torque region, and in this way we can still more aggressively. We still have to aggressively gear the motor, but we don't lose as much high-end top speed because of the high RPM of the MRAX 228. So we can still achieve a performance without hindering the motor's structural integrity. But and that being said, with this more aggressive gearing, we get more overall torque to the wheels if we ever do get into that peak torque region, which gives us overall faster acceleration off the line.
Gotcha. Okay. So, what type of gear train did you guys end up choosing for the driveline? Like, why that specific configuration?
So our decision was based mostly off of packaging. As I said before, that was a huge concern for us. So we chose a double reduction spur design. So 4 gears, 2 reductions. Double reduction because you can fit a bigger reduction in a smaller space. As I said, we had a really small volume constraint, so we managed to jam a large reduction into a small space given that design. And then we use spur gears just because they're efficient, they're easy to manufacture, and it avoids having to design for, because if you use, for example, if you use like helical gear, you end up with axial loads on the shaft. So there's more consideration based in the design and the bearing selection, that kind of thing, that we were able to completely eliminate just by going with a basic spur gear design. And spur gears are often avoided mostly because they're loud, but noise isn't really a concern for us. So we chose to pursue that method. So that was sort of our methodology for choosing the high level gear train design.
So we're back here with Aiden and Luke, and we've covered a lot of the design process. So we're going to just talk a little bit about manufacturing. So Luke, do you want to take us through a little bit of the manufacturing process for the gears this year?
Yeah, for sure. So our gears this year were manufactured by Linamar, who's our sponsor. Here are the green gears they call them, which means that they're untreated. So the first thing they did was just machine the overall blank profile, which is just the outer diameter and then the inner diameter with these weight-saving pockets and these holes. And then they would proceed to manufacture these splines by a wire EDM. And then they would cut the teeth on a hobbing machine, they call them. And then after that, they would take their take CMMs and other quality and analytics machines, and they would just trace over these profiles and make sure that they were all to spec, and as well gather this data for after heat treating to make sure that they didn't distort too much from the high heat. And so here's an example of a heat treated gear that was out of spec. So they basically use a carburizing flame or a gas carburizing flame, and they create a hardened profile on the outside so the teeth can take much more contact stress. And so that's how these are manufactured. And then they would also analyze these again to make sure that they didn't distort over the heat treating process.
So what about the rest of the components of the gearbox, like the housing and all of that? Can you chat a little bit about how that went? Well,
the shafts were manufactured in a similar way to the gears. They were turned on a CNC lathe, and then they were cut with the external splines that we showed there. And then they were heat treated in a similar fashion. Whereas the housing was manufactured by Bryac Machining, and it was a CNC aluminum housing in 2 pieces, and it's made of 7075, which is like a high-grade aircraft grade material that has a very high tensile strength.
Okay, and then finally, can you just walk us through, what's the driveline going to look like for next year? Kind of what is your guys' vision to pass on to the future teams?
Yeah, so we set out with one of our goals was we wanted this gearbox to be usable for several years in the future to sort of allow other areas of the car to get developed in case no changes are made to the drivetrain in the next couple of years. But ideally, so the next step in the process would be the idea would be right now we run 1 motor that feeds the whole rear axle, but the next step would be run 2 motors in the rear for the feeding that same axle. Which would require obviously another gearbox, and then after that, the next step would be sort of like the final step would be running in-hub motors in all 4 wheels, which would require probably planetary gear sets, and so that would be another development in the gearbox life cycle of the team would be getting to the stage where we have planetary gearboxes in all four wheels, which allows for a lot of really cool and interesting sort of traction control systems and that kind of thing. And then having four-wheel drive is a huge benefit as well. So that would be that's sort of the holy grail for drivetrain.
Yeah.
Now that we're electric, so it's we're looking forward to seeing what the team's going to be able to do in the future.
Absolutely. Well, it sounds like you guys have set them up pretty well for success. There's been a lot of good developments this year. So
Hopefully.
Thanks, guys. Really appreciate your time.
Thank you very much.
Aiden and Luke, guys, thanks for tuning in, and we'll see you next time. Hi everyone, so we're back with the next series of our videos for the 2019 season, just highlighting some of the subsections for the WFR 19E. Today we're joined by Grant Leishman, who's the subsection lead for our chassis. Thanks for coming on, Grant. Really appreciate it.
Good to see you, Alex. Thank you.
So yeah, this was a big undertaking for this year. The first time we've had full monocoque for the team. Why did you choose this year particularly to attempt the first full monocoque design?
So there was a lot of reasons. I think first and foremost was kind of that we wanted to kind of take on a real challenge and learn as much as we possibly could. Then also we were kind of following the logical progression of the chassis. So 2015 we had our first monocoque. 2017 we removed some of the steel tube frame in the rear, replaced it with composite materials. And of course this year we replaced the entire steel tube subframe for the full monocoque, kind of completing the design timeline, I suppose. We had a lot of composite experience on the team this year, including about 10 years of cumulative chassis experience, including myself and two other ex-leads. So a lot of experience to draw on. And then of course, switching to EV got rid of a lot of the hurdles that we were kind of coming across when we were thinking about going with a full monocoque for an internal combustion engine. So.
Good. Well, it sounds like it was quite an undertaking and good timely, with the EV transition.
Perfect timing.
So, okay, then so kind of what was your main focus in designing and building the chassis this year in terms of integration, weight, things like that?
So emphasis always on safety, maximizing safety and minimizing mass, of course. But then also this year we had a great opportunity to kind of look a lot at integration. And that came mostly from the fact that we're doing a full redesign from the ground up essentially. And just allowed us to kind of look at previous years and draw on our experience and kind of make sure that the integration for this car was the best the team has ever seen.
And obviously this was a challenging undertaking. You said this is the first time we're doing this. So what are some of the challenges, both anticipated and not, that the chassis team was presented with this year?
So the timeline for the full monocoque wasn't that we had anticipated, but me myself, I didn't really respect how difficult it would be to kind of complete some of these goals. I was passing a full course load. So just designing brand new geometry, integrating the new EV powertrain, a brand new set of molds to design and prep and then lay up schedules. That with exams and assignments, of course, is a daunting task. So luckily I made it through. And then also making sure that we have all our rules, knowledge enough, and that we could pay really close attention to everything and then make it through our technical inspection with a safe and competitive vehicle.
Yeah, I guess that's the thing is to make sure it's not only fast, but that it abides by the rules. So, so what do you think for this year makes this monocoque special? Like, what's going to make it stand out with the other teams?
So, I guess at a first glance, the first thing that you see is that we're running a full planar design, which is something that not a lot of teams do. Typically, they'll pull on certain elements, but we're one of the few teams that kind of goes for the full monocoque, that's planar, and that kind of extends to the rest of the aesthetic on the car. A lot of other subsystems will kind of draw that into the components in their car, and then once they're mounted, it really does kind of pull everything together and it looks very clean. Another thing that not a lot of teams are doing as well is that we're dropping our accumulator through the floor, and so our rationale for that was that we don't want to put any of our members in a situation where they might have to awkwardly lift a really heavy pack through the firewall, or the design challenges that would come with a full monocoque and removing it through a rear plane.
Right.
So we actually integrated that into our accumulator cart, and so we actually installed a jack that would come up towards the accumulator and then lower it down with a mechanical advantage. So at no point between dropping it from the car and moving it to a battery charging station, at no point does anybody have to lift the pack.
Wow, that's certainly a convenient design, right? You always think about the servicing, not just the manufacturing and the design stage. For sure. Hi everybody, so we're back here with Grant, still talking about the chassis for the WFR 19E. So Grant, you talked a little bit earlier about the need for integration of the chassis with the new EV system. So what are some of the areas that highlight the integration with the rest of the vehicle and the other subsystems?
There's a lot of things, but some of my favorites, I'd probably say that the swept rear frame that kind of accommodates the proper angle for our diffuser and our under tray was definitely a good one that we kind of worked on from day one with the aero lead. I'm really glad that made it onto the car. The front suspension, having everything on one plane, definitely reduced the complexity of the kinematics that they were having to deal with and definitely gave them a little bit more room for iteration in future years. We have a very narrow cross section, which allows us to have a very narrow track width, which is very beneficial. And then of course we have a lot of pocketing in our core throughout the monocoque, which allows us to kind of maximize the amount of space that we have for packaging, and then also drop our CG in a couple places, like we're able to drop the driver a full inch to the lowest point in the car, which actually is quite a considerable amount in CG.
Yeah, I guess, I mean, chassis implicitly is one of those systems that has to integrate with every other subsystem because everything's basically being housed on the car. So I'm sure it was a big design challenge. So what would you say, kind of to sum everything up, what would you say you're most proud of on the chassis design and the manufacturing process for this season?
Honestly, this year, I'd say the thing that I'm most proud of was just the commitment from the entire team to make sure that we had a full monocoque at the end of the build season. Like, I couldn't be more impressed, honestly. I found myself pulling a lot of late nights next to other subsystem leads, really committed members, and some really fantastic recruits. I could not have done it without them. Honestly, I just really like to thank them for all of their support and their generosity with their time. And I'm just so excited to see the monocoque compete at Formula North in Lincoln this year.
Yeah, I think everyone's going to be excited. We're all excited as well, and hopefully you'll join us there. We've got Grant Leishman, so thanks for joining us, Grant. Really appreciate it. Thanks for your time, and tune in for the next one, guys. See you soon. Hi everybody, so we're back here on our series of videos for the 2019 season with the Western Formula Racing team. We're talking to a few of the subsection team leads about their subsections and how they're contributing to the WFR 19E for our season. We've got Alex Peroni and Ian Stother with us from the electrical team. So thanks guys for joining us today, really appreciate it. So I guess let's start with the high level picture. How would you describe your design methodology and the kind of focus for this year, Alex?
I guess for this year in the switch to EV, we mainly wanted to focus on making a vehicle that was simple, that had components that all integrated with each other very well, and wanted to be very robust and high performing. So to give you an example of simplicity, we could have chose to do a traction control system that was based off state space logic, but we went with a more conventional PID approach that's tried and true and should perform well. Okay. For an example of integration, we chose our motor inverter BMS system that integrated with each other, as well as like chargers that all integrated well with each other out of the box, so that we knew that we'd be successful going into the future. And in terms of robustness, we have backup systems and like fail-safes for the control logic of our vehicle to ensure that in the event of a tracking system failure, if say a wheel speed goes out, we have a fail-safe in place to just go into direct torque drive mode for the vehicle, as opposed to stopping and not functioning.
So obviously a lot of work's gone into the design process and a lot of thought put into that. So what, Ian, if you could take us through maybe what are some of the performance benefits you hope that the team will achieve with the new EV powertrain strategy over kind of our ICE approach last year?
Yeah, so one of the nice things is that since we have so much control over how the car thinks with our controller, we can tune a lot of the parameters to be specific to the vehicle. So we can estimate what kind of slip the car will be going through based off of our traction profile. We can also integrate a lot of the feedback from the drivers to tune the vehicle response the way they want it. So we can tune the snappier response, we can tune how the accelerator pedal responds to them. And we can essentially look at anything the car can see, we can integrate that to how the car behaves. So we can account for all sorts of factors in how the car performs.
So we're back here with Ian and Alex, still chatting about the EV powertrain. Tell me, Alex, like what are the main factors I think that are the most unique about the system that we've designed for this year?
I guess I'd say what the most unique component of our vehicle is that is our vehicle controller. And for that, we're using the Motec M150. In a previous year, competition bought the Motec as an engine controller for our vehicle. And what we found with it is that with the development license that we purchased with the controller, we were able to completely rewrite the firmware for the device. And with that, what we were able to do actually is completely gut out all of the internal combustion engine code and rewrite the firmware for an electric vehicle. This allowed us to have like cost savings, and it's probably as far as we know, only one other team, and not even an FSAE team, has been able to rewrite the firmware for that for an electric vehicle in the past. Now, in terms of other things that we're doing that's unique, we have, for the first time this year, wireless telemetry over Wi-Fi. And what that's connecting is through the serial on our Reinhardt. We have that on Wi-Fi, as well as direct connection to our Motec controller. And through that, actually, because all of the devices on our car, or over 7 devices on our car, are connected through CAN communication, we're able to get live telemetry data on almost every system on our vehicle, including the battery management system, information that we get to our dashboard, and specifically the communication between the ECU and the Reinhardt drive.
So again, a big principle of integrating all the systems for simplicity and efficiency. It's it's good. So what, Ian, kind of tell me what if anything have you guys done differently in terms of the manufacturing part sourcing this year? Because obviously that's a large part that follows up the design phase and needs to run pretty well.
Yeah, absolutely. So one of the biggest challenges we had this year was the sheer amount of components we ordered. So if you looked at the electrical system in previous years, maybe it were between 20 to 30 components. This year we ordered around 2,000 unique components. So just tracking all of that and centralizing the tracking of that. And then also, like, one of the other things we did in addition to centralizing the tracking was we implemented a lot of tools that were available to us through just free tools such as Octopart. We were able to take one part number, punch it into a database, and then locate the cheapest source for that part. And so one of the things we did to keep costs down in terms of shipping is we amalgamated all our parts into 3 big orders for 3 main suppliers. And so that kind of cut down on shipping, and then also just made it a bit easier to keep track of things. So that's one of the biggest differences in terms of sourcing. In terms of manufacturing, obviously, since we're building a lot of new systems, like new custom circuit boards, what we've done is we ordered them ahead of time, tested them out early on, just because circuit boards are very interesting to design, and that it's almost like programming a physical thing. So
sure, yeah.
For most people who've programmed, they probably experience that it never works the first time. So it's good to get the board there together, solder it together, test it, and make sure it works, identify what the issues are, and then go for a reprint. And then your next board should be perfect.
For sure. So obviously a lot of moving parts and a lot of moving components. What do you think, Alex, has been the biggest challenge for the electrical team face going into the year?
I guess in terms of challenges for 2019, the biggest would be dealing with the whole problem of the accumulator. Now, with being the first team electrical vehicle and dealing with a 400 volt battery, that could be daunting at first in terms of a safety perspective and getting yourself educated on how to deal with that, and in terms of a sourcing and fusing perspective. Now, for sourcing, we had to go through many different cells to find cells that, at the voltage we wanted, allowed for an efficient energy density as well as power density, and not only that, fit in the package that, in rear packaging. Now, after all that was dealt with, we still had the fusing problem. Now, as a first-year team, it's hard to develop a fusing methodology on top of all the other tasks we have to do for an EV, in terms of testing fusing and actually getting the equipment in-house to reliably fuse every single cell and ensure that we're not going to have any failures at competition. What we ended up doing was going with pre-built Energy cells that do the cell balancing and fusing for you, so that we just have to connect to the bus in series in the very end, and that helped take a little bit of the focus off of that challenge and allow us to focus more of our time and effort on the traction control system.
So it was obviously a very large change from last year and a huge development push, a very complex system all in itself. So why choose a single motor? What was the reasoning behind that?
Yeah, so one of the main issues when you're building a new system is that, as you mentioned before, we want to keep it simple. So in an effort to keep it simple, we sourced a lot of parts that were pre-manufactured. So our drives off the shelf, our motors off the shelf, even our battery pack for the most part is off the shelf components integrated together. And so when you look at the available motor drives on the market right now, most of them are geared towards either consumer cars or larger vehicles in the one we're building. So if you're gonna build a drive for a dual motor system, you would need to build your own inverter in terms of, or to make sense in terms of weight. So ours is fairly light compared to other drives in a similar power class, but there's not many inverters available at lower power class than we have, just because of the size of it. So that was one of the main reasons, was it just made sense of vehicle weight. And then in addition to that, we look at others who made this transition. A lot of them found it difficult to go ahead and immediately start with 2 or 4 motors. There's a lot of problems technically with that. It's more complicated. There's a lot more programming involved. So it's much easier to transition from a internal combustion engine straight to a cylinder, because we're plugging into roll differential through the new gearbox. And testing can be done on the old dyno we used to use. So it just made a lot of sense in terms of how complex it was going to be, and then just dealing with all the other moving parts. So integrating all the small systems I was talking about earlier, and making sure everything's going to work well for the car.
Sure. So again, I think going back to our team philosophy of the season, kind of simplicity, integration, performance, kind of all in one package, not jumping too far ahead in the development stage.
Absolutely.
I think is hopefully going to help us out throughout the season. So why specifically the 400 volts system? Why did you go with that?
I guess that's a loaded question, in that it was a big team integration was required to choose that system voltage. And the reason being for that is you'll find when creating an accumulator, dependent on the package that you have to work with in terms of sizing and physical layout, you have to deal with the different types of cells you want to use, pouch versus cylindrical, the type of cylindrical. And with that, you can have different layouts of those cells, and with those different layouts and different voltages.
You guys join us on a beautiful spring day for what's an absolutely amazing and historic event in our team's 30-year history, the launch of our first ever electric vehicle. So my name is Alex Slonim. I'm going to be your host for this afternoon. Alongside me are 2 very talented gentlemen, our Director of Team Operations, Julian Bertone, who clearly has a lot more fans than me, and our Technical Director, Dean Kernahan. So they're going to be taking you through some strategy and technical presentations this afternoon, and I will have the distinct pleasure of introducing some of our distinguished sponsors and amazing alumni that have contributed to the long-term success of our team. I firstly really want to thank all of our partners, our sponsors, our alumni, and our team advisors, and of course our friends and family. We're very sorry you haven't seen us for a while, so we will be back. But without your guys' support, this would not be possible for us, and our vision could not be realized. So a huge thank you to you. I also really want to thank Western University and, of course, the remarkable Windy Research Institute for hosting this event for a second year in a row. So give a big round of applause for them as well. It's a great facility. Hopefully you guys have had a chance to try out the racing simulator a little bit and have some snacks and check out the subsection lead interviews that we've posted. They will be available online on YouTube, on our YouTube channel as well. And we really hope that you can join us at our guest reception later on this afternoon. And now I'm going to hand it over to somebody a lot more capable than I. Julian's going to take you through a little bit of history on the team and our 2018 year in review. Julian.
Thanks, Alex. Before we start, a quick note. My throat's a little bit messed up, so I get the honor of using this echoey microphone. With that, I'm expecting my voice to fluctuate between the deep raspiness of an old man and the voice cracks of a prepubescent boy. There you go. So I'd only ask, if at all possible, please save your laughter till the end. So I'm going to go through today a little presentation outlining our 2017-2018 season, and I'm going to talk a little bit about what we've been up to since the last time we gathered here at the Windy Dome. So, Formula One, right? This is a question that we get a lot on the team, and I've come to learn over the last 5 years that what we do is pretty unique. Whether the fact that we're all students, that we spend more time designing and building than we do racing, or the fact that we tear down the car and start it from scratch every single year. So I thought I'd start off by going over what our team is, what we do, and then we'll go into the presentation. So we're a Formula SAE team, which means we compete in the Formula League put on by the Society of Automotive Engineers. We're made up of 30 to 60 students, so 30 core students that take responsibility for subsystems, whether it be designing, manufacturing, or planning events, and 30 other students that help out when they can in whatever capacity they can. Our motto are the 3 E's: excellence, endurance, enthusiasm. We use this motto to guide all of our decisions on the team, whether it's our high-level strategy for the year, tough competition calls, or the actual design of the vehicle. They stand for excellence, to create highly skilled and effective professionals, endurance, to ensure the long-term success of the team, and enthusiasm, to have fun. One thing I'd also like to note is we're open to all faculties. Due to the scope of our project, we have a lot of engineers, but we're open to everyone at Western, and I'm glad to point out Alex as an example. Alex is a law student that joined the team a couple of years ago, and not only is he a great MC, but he's turned himself into one of the top laminators on our team, helping make our carbon fiber monocoque and our aerodynamic elements. So what do? Every year our team takes on the crazy task of designing, building, and racing a Formula-style one-seater race car in just 8 months. We do it all to build skills from the soft, the leadership, the scheduling, all the way to the engineering and the technical. Our competitions are against 500 other teams from around the world, and they consist of a variety of events. Among them, the design event, where we show off our designs and try to prove to our judges that we have the best car there. We have the cost report, where we cost out our car down to the nut and bolt. The business pitch, I'm just gonna ditch the mic. The business pitch, where we pitch our car as if it's an investment and we're gonna make 500 of them. And obviously the dynamic events, ranging from acceleration to the skid pad, the autocross, and finally a grueling 22-kilometer race against 100 other cars at any given competition. But at the end of the day, our team is really just a mechanism to take very excited, very engaged, but unskilled first-year recruits, and turn them into the leaders and engineers of tomorrow. As you can see from these pictures, we like to teach very technical skills like welding, laminating, fixing parts we messed up, and putting together the pedals. I really like this slide because not only does it show some of our members, but it shows the fantastic companies that we went to work for last summer. And I love this slide even more because a lot of those companies are our sponsors. I really think it's a testament that not only do our sponsors support us, but they go on to become our employers, our mentors, and our colleagues. And I think that's a really great part of the team. So that's who we are. What have we been up to? Every year starts with our unveiling. These are pictures from last year's unveiling. We love unveiling because not only do we get to hang out in one of the nicest buildings that Western owns, but we also get to celebrate with everyone that made the car happen. Another thing that we really love doing throughout the year is meeting all of our sponsors, whether it's giving them a tour of our shop, us touring one of their world-class facilities, or just stopping by to hand over a thank you plaque. There's nothing we love better than walking in, meeting the people that actually make our car happen, and seeing the plaque from last year sitting in their reception. Another event that we love to host is the Extended Team Drive Day, where we let our sponsors and our alumni actually take a drive in our car. As you can see this year, we were blessed with our typical perfect tropical London weather. But all jokes aside, this was a great event. We also merged it for another time with our design event, where our sponsors critiqued our design, prepared our subsystem leads for competition by really putting them through their paces and testing their skills, and helped us actually shape the 2019 car. Another thing we like to do is outreach. So believe it or not, we don't just live in the shop all the time. This year we had the pleasure of doing a variety of outreach, whether it was hosting Go Eng Girl, the Western Engineering Girls Club, showing prospective grade 12 students the shop, telling them about Western, and really getting them hooked on science, technology, engineering, and math as a major, or actually going to a school and speaking to a bunch of grade 3s and grade 4s, and getting them visibly very excited about the possibility of one day being on a race car team. A lot of people think we do this to give back to the community. Really, we're just building the pipeline for the 2028 team. Recruitment's really hard. You got to do what you got to do. And finally, the event that we go to is SAE Students Night. This is an event in Toronto where we go over our car, present some engineering challenges that we overcame throughout the year, and speak to judges and try to convince them that we're a team that's better than all the others with regards to our scheduling, planning, and our design process. There was some debate about whether or not we should include this slide. It's not a very good picture, it's very grainy, and I'm doing something very weird with my right arm in it. But but we took home the first place for the second year in a row. Won ourselves $1,000 for some pizza and tires, so I thought it was worth putting on there. So, a little recap on the car that we built last year, the 2018 car. Last year we saw the introduction of our front outboard suspension, which you can see in the top left there. We brought the suspension outside of the car so we could tune it better on race day. We made leaps and bounds in our carbon fiber rim development, which has been going on for a few years. We also pioneered super wide tires, so 9-inch tires in FSE are something that hadn't been done before our team last year. So that was a big leap that we validated and found worked very well for us. And finally, we upgraded our data acquisition system to a MOTEC, which really helped our tuning and our live data analysis on race day. All in all, last year we built one hell of a car. Every year, we try not to start from scratch. We try to really learn from past years. And not only do we learn from the 2018 car, but it really set the standard high with regards to build quality, aesthetics, and performance. So we were very happy and very nervous to follow in the footsteps of the 2018 car, but we're really proud of what we accomplished last year. So, at the end of the day, we do build the car to compete, so I'll go over some of our competitions. It all starts with FSA Michigan, which is our flagship 80 car, most competitive in North America competition. I'm very happy to say that we came first place in the business case, which means that Western had the most competitive and best business presentation in North America last year. That's something that we're very proud of. And we also came 12th place in design, which means we got second place in our queue. We're very proud of this specifically because we always get placed in a very competitive queue because of our historical design performance. So this was a great competition for us. Next, we go to Formula North right here in Barrie. Here we placed second place in the business competition. I thought we still did pretty good, but business is subjective after all. And we also got third place in the design event. This was really significant because it means we got to design finals, which means we got into the second round of much more intense judging, where some of the industry's best engineers put us through our paces for 1 full hour and really got down to the nitty-gritty of our car to see what we were made of. So North was a great competition for us. Next, we drove 16 hours out to FSA Lincoln to compete under the Nebraskan sun. I'm glad to say we got 9th place in design, which was great because we cracked the top 10. And there's also a bonus race event afterwards, which was the Sports Car Club of America Autocross. And we actually had the fastest time of the day, beating out a lot of the other Formula cars that competed in Lincoln. Finally, every year we wrap up our season with our shootout events, where there's no design, no endurance, it's just the hottest lap of the day wins. In Toronto, we got 15th place due to some engine issues, but we finished off at Pittsburgh with 4th place overall, which was a great reminder that we did build a competitive car that really could race and beat other teams. As we look back on the 2017-2018 season, we learned a lot, we had a lot of fun. I'm very proud to say that we had a 5-competition season, which means we raced through the whole summer, which was great. The team grew in numbers, we did some really good recruitment, and we're very happy with it. Going through the year in review, though, there are a couple things that are to be desired that we wish we could say that we achieved. And they really set the stage and motivated us to work even harder in 2019. I really think we came through and did just that. One thing's for sure, though, none of this would be possible without our supporters, whether it's our sponsors, the people that help us out in a pinch, or our families. So on behalf of the team, I want to thank each and every one of you for supporting us in 2017-2018. We really do appreciate it. I tried to make this presentation pretty interesting and throw a bunch of pictures in, but nothing does it justice like a hype video. So I'll have you all join me to watch a video that Paul Davenport put together for us here today. Thank you.
That's an awesome video. Thanks, Paul. Yeah, obviously a video speaks 1,000 words. But as you guys know, in our 30-year history, the team's not and the car's not built in a year. And without the support of a lot of our sponsors and especially our dedicated alumni advisors, we wouldn't be able to achieve the progress and the technical development that we have to date. So with that said, I want to welcome a couple of those representatives over today. The first one's a project manager from Diamond Aircraft. He's been a key advisor to a lot of the senior members, as well as our alumni, as well as representing one of our biggest and most valued sponsors. So I want to welcome up Matthew Hessel, Western Engineering, class of 2007.
So the first line in my speech had, "Doesn't the car look great?" But I guess that's because I didn't know I was going before the car. A shout out though to Sean Kelly, who's here when it comes up. He did the painting, and I think everyone can agree that it's looking sharp. So Diamond Aircraft, our relationship with the Formula team started in 2015 when George K asked for some free stuff. And then said, hey, we got some students that you can have as well for the summer. So we hired 4 students that summer and have been hiring students ever since. For multiple years, we had the privilege of hiring these 2 good-looking guys back here, Julian and Dean. Julian worked with us, and he developed some software solutions that are still being used to this day, adding value to multiple departments. And Dean did 4 summers with us and in engineering, and helped design an air vehicle for Northrop Grumman that is flying today, and which the customers are real happy with. These 2 demonstrated the ideal qualities of a team player. They were hungry, humble, and smart, and we were honored to have them. But in general, the partnership that we have with the team and they have with industry in general is nothing short of a win-win situation. So what does industry get? Well, we get young, motivated, intelligent, cheap minds and hearts that we can use, whether it's for creating a project that we didn't have time for, or whether it's just covering for vacation schedules in the summer. So that's what industry gets. Well, what do the students get? Well, the students get paid work. For the summer, they get a chance to work in an environment, in Diamond's case, that has a design and manufacturing all in one. They get to work around airplanes in our case, which is pretty cool. And hopefully they get some coaching from their leader and a great thing to write on their resume that gives them a leg up compared to everyone else who doesn't get that, who works at Wendy's. The team also wins because these relationships are formed over years and they get free stuff. Diamond's happy to give labor and materials. And also the team members become kind of a hot commodity. For us, it's the first place we look for summer students. For me, I started in 2004 at Diamond, and I got a chance to prove myself, and it's turned into a 15-year career for me. So it's win-win all over the place. So we at Diamond have moved beyond the summer co-op position, and we're also starting to take on interns. We've got 12 to 16 months placements now, starting next month in engineering, operations, and finance within the company. And so a shout out to any industry partners out there Both these programs, the summer co-op and the internship, are highly valuable and well worth your time. So to the team, in closing, congratulations. This is quite the accomplishment that I can see. And a big year for you guys. Moving electric, it was no small accomplishment. So congratulations to you guys. The work is not done. The competitions are still coming. And so I encourage you guys in the months ahead and in the years ahead to seek to embody the characteristics of an ideal team player. Continue to be hungry. Never stop learning, never stop improving, never stop trying new things. Be humble, recognize, and I think from my experience with the team, you guys do a great job of this. Your success is the team's success. And be smart, realize that we're all people and we all do things differently, and so be people smart. Find the best ways of working together to accomplish the greater good. That's all. Congratulations and best of luck in this season.
Thanks, Matt. Thanks very much, Matthew. It's always great to hear from our alumni as well as our sponsors for how valuable not only they are to the team, but how valuable we are to them. So with that said, I want to ask up another one of our not only Western Edge alumni, but a team alumni as well. He is no stranger to leadership, having led the suspension team in 2015 and then becoming a team lead in 16 and 17, currently working for the Boston Consulting Group, very prestigious. Huge congratulations. I want to welcome up Chris Corniss, Western Engineering class of 2017.
So first of all, I want to say thank you for having us and for continuing this tradition. This is very exciting for all of us, particularly alumni. So thank you, and I can speak for everyone when I say we're very excited to see the first electric Western Formula racing car. So thanks for having us, guys. So what I wanted to talk about today was what we're celebrating, because one part of what we're celebrating is what this team has built, like the car, like the manifestation of the work over the last year. But also we're celebrating a lot more. We're celebrating like the personal development of each and every team member throughout the year. And I think as an alumni, reflecting back on my time at Western, I think that's one of the biggest takeaways for me. And to start with one of the most obvious and one of the most visible of those personal accomplishments is what this enables for you guys from a job and recruiting perspective. I think Matt spoke to it partially, but it's really like the world's your oyster. Like you guys have so many different opportunities, and if you look at the alumni and the jobs that people work at, I think that speaks volumes. You have people who work at the prestigious companies, the OEMs of the world, the Diamonds, the Multimatics, the JMPs. You have people who worked in the high-tech world. We have people on the phone today who are out in San Francisco working for the Boring Company, working for some company that's building self-driving cars. We won't say who it is just yet. You have people also chasing passions. We have alumni in Formula One. We have alumni chasing higher education. And we also have alumni who, for reasons I really respect and I don't think I fully understood when I graduated, but resonate with me now, have made constraints personal, geographic, and found great jobs within those constraints that let them live the lifestyle they want to live. And I think that's very important. And I can say that not everyone is so blessed with those opportunities. So you guys have earned that. And of course, how you've earned that is the skill set that you learn and develop a year on this team. I mean, there's the technical skill set that you guys have developed, and I think that's obvious and goes without saying. But there's so much more. You also have the leadership skills that everyone's learned, from managing just the design of your own project, to designing a subsystem, to leading events on the non-technical team, to eventually leading the team. The leadership lessons you learn along the way are so important, and the teamwork too. To imagine a group of, I don't know how big the team is now, 40, 50 people stuffed in a shop, fueled off Monster Energy drinks at 4 a.m. Like the amount of teamwork lessons that you have to learn to thrive in that environment is quite incredible. And I think another one that often doesn't get mentioned is the humility and general maturity that you develop on this team. I mean, the reality is you make a lot of mistakes. I've, on my time on the team, made tons. One that I remembered, you guys were talking about design finals, and the very first time I was on the team that made design finals, I remember being so excited. I was finally going to present my suspension. We made design finals. This is like the biggest accomplishment. Like, we were going to prove our design, and we broke, the suspension I designed broke like half an hour before design finals. So we had to carry the car into design finals so that it couldn't even roll. And I'm here to present to like these industry professionals why this is the best suspension in the competition. And the car can't even roll, so. You're going to make tons of mistakes, but I think, and you'll reflect back on your time with all these things you wish you'd done differently, but I think that's exactly what makes it such a good experience, is you learn from failure, and it's such a good environment to learn from failure. And to some extent, that's unique to Formula. And I think the other thing that's worth celebrating beyond the professions that you guys and the career paths you have and the skills you've learned is also the friendships you guys have developed. If you were to design a social experiment to develop the strongest friendships possible, I think this is what you would design. You take a whole bunch of deeply motivated and passionate people, you put them on an ambiguous and challenging problem for a year in this like super high stress environment, working crazy hours for a long, long time. And then it's still super exciting and fun, and the friendships that you have, you'll celebrate for a long time. I can speak for myself personally. I've been to friends' weddings, cottage weekends, and I think the alumni group here can speak to the fact that, I mean, there's so many of us here, tells you how strong the bond and connection is between all of us. And not to plug for the after party, but of course there's the alumni events going on tonight as well. It's just such a strong friendship. So in closing, I wanted to say that we're here today to obviously celebrate what looks like quite an incredible car and quite an incredible technical achievement. But in reality, there's a lot of personal sides of this team that we should be celebrating as well today, too. Thanks.
Thank you so much, Chris. We're now going to go do our final presentation. We're going to talk a little bit about going electric, why we did it, how we did it, and then we're going to talk about our car and why we think it's Western Formula Racing's first electric car, but also the best car that we've had yet. Give the projector 1 sec to catch up here, otherwise I'll walk over to the other side. Nice. All right, so as most of you should know, and if not, I hope the huge purple lightning bolt on the title slide gave it away, but we are going electric this year. In June, the team started to discuss going electric. A couple people brought it up. I know Dean, myself, a lot of other senior team members were very quick to dismiss it. We didn't want to take on such a big challenge, but we ended up entertaining the thought as a team. We spoke about it, we did some polling, and in July we made a decision to pursue the first electric car ever. Given some constraints that we would pick out our motor, our gearbox, our batteries, and a couple other things by September 1st so that we could have a running start to the season. By September 1st, we'd hit those milestones and actually a couple more, thanks to some fantastic dedication from the team over the summer. 8 months later, we're here. We've designed it, we've built it, and we think we have something pretty awesome to unveil. Today I'm going to go through a little bit of, shed a little bit more light on why we did it, and how we chose to make this huge leap, not only for the car, but for the team, and develop the car and the infrastructure to support it for years to come. So the first thing we wanted to look at was, why do people want to go EV? So as engineers, we decided to poll the team and get some data, because that's the only way to do it. And we found that half of the team almost wanted it purely for the sake of being on the cutting edge. As a team, we believe that electric is the future of mobility, and we wanted to make sure that our grads get a seat at the table and can pursue the absolute bleeding edge of technology and make the world better. Another 20% of the team really liked the pragmatic, the resource alignment aspect, which was that not only do we have a fantastic electrical team that could support this, but we had a fantastic mechanical team that could support all the other things that you need to make an electric traction system possible. And finally, I don't know who these were, but some crazy 10% of the students thought, you know what, building and designing a car in 8 months isn't hard enough usually. I really want to take on the extra challenge of doing it, but with electrons instead of gasoline. So that's why we wanted to do it. So as senior management, we decided to formally make a decision. But knowing this was so monumental for the team, we didn't want to just jump right into it. Our goal is to make a decision in a way that would be consistent with a world-class organization. And for us, that meant that it had to be transparent, data-driven, objective, and democratic-ish. For us, what that meant was everyone on the team would vote, and to their discretion, they would assign themselves a weight to their vote based on how much they thought the decision would affect them personally. And we thought this was a really good way to do it because it really matched the very flexible and kind of varying nature of commitment on our team. Looking at the data was actually very interesting, but also a little bit troubling. As received, about 58% of the team wanted to go electric, which was promising. But the pure Democratic vote was 50-50 right down the middle, which was worrying because we knew that without the full support of the team, we wouldn't be able to perform either on the combustion or the electric side. Everyone needed to be engaged. And then we also opened up the vote to alumni and sponsors and such. And when we filtered it to only the 2019 team, what we found is that it was actually higher. It was almost 3/4 of the team wanted to go EV. And what this meant was that a lot of alumni that knew a lot more than us had very cold feet. A lot of the people that got filtered out were the people on internship that are coming back next year. And they didn't want to inherit a mess. They didn't want us to try it out and leave them with something that they couldn't use in the future. So moving forward from this, we knew that we really had to take the decision carefully. So we looked at the reasons why people didn't want to go to EV. The main one was reliability. As our team knows, very painfully, if the car isn't reliable, you can't race it, and it makes race day a whole lot less fun. The three main risks that people outlined on reliability was that we had no knowledge of building an electric car. We had no experience with the actual FSE electric competition, which introduces hundreds of new rules, regulations, and technical requirements. And finally, we've had systematic team issues with reliability, as any Formula team does. So what we did as senior management was figure out how we could mitigate that before we moved forward. To mitigate the knowledge risk, we reached out to faculty, created a network of both electrical and mechanical engineering profs that we could draw on throughout the year, as well as make connections with alumni that said their doors would be open and their phones would be on if we ever wanted to chat about our design and get some advice. On the experience side, we reached out to 4 world-class electric teams. And they were very welcoming, and they helped us out through the design phase, telling us what they did wrong, helping us learn from their lessons, and giving us some advice on what would work and what just wouldn't. And finally, something that we implemented to help curb the team issues with reliability was a intensive 2-part review system. So no design or major order went out without having 2 people that did not work on the design review it before it went out. It took a bit more time to get some of the things out, but I think we really reaped the benefits in the manufacturing phase when we found that things went together a little bit smoother than usual because a lot of the issues had been hashed out early. The other big risk was that we wanted to compete, and electric posed a risk on the competing front as well. Last year, teams that wouldn't even have a rolling car would break the top 5 because there would only be 5 electric cars. As a team, this didn't sit well with us because we wanted to be on the absolute cutting edge, and we wanted to do something that would be worth talking about and not just show up and get a medal. And the other thing was Michigan is yet to convert over to electric, and we were very sad about losing our flagship competition. So what we did on the on the fact that it would be too small, what we did on that front was we did a little bit of research, spoke to some teams, and we took a leap of faith. We thought that a lot more teams would register, and we were very happy to find that both competitions, FSA North and Electric, were oversubscribed. So we're going to compete against at least 30 to 50 teams at each one, which was great for the team. We chose a really good year to switch. And as far as Michigan, we've spoken to the organizers. We're confident it'll go electric in the next couple years. And in the meantime, we've chosen as a team to still attend so that we can mingle with other teams, get the experience, and be spectators at the event. So after all this, a grueling summer of hitting our milestones, having our traction team figure out our batteries, our gearbox, our motor over the summer, making a very tough team decision. and then 8 months of grueling work on the design and manufacturing side, we chose to go electric, and we think we pulled it off. So I'm very excited now to pass it off to Dean, who's going to go over why we think this is the highest performing Western Formula Racing car ever. So here it is, Dean.
Well, thank you so much, Julian. Thank you, Matt. Thank you, Chris. Thank you, Alex. You're all also incredible presenters. I'm the technical guy, so bear with me. But some things I did want to highlight for this year. Often when we showcase a car, it's really difficult to communicate just the sheer scope involved in the project. So some things to highlight: we have over 100 members that have contributed in some capacity to this vehicle. We have 10 faculty members that have helped us. We have 65 unique sponsors and just under 1,000 unique components on the vehicle. So yeah, just some incredible things from a scope standpoint. Now, at the beginning of the year, we sat down with all of our subsystem leads, and we got them to write out things that they thought would be on an awesome car, on an awesome vehicle design. And by taking that information and kind of compiling it, we were able to develop 3 design goals. That's simplicity, integration, and performance. Simplicity, we're building the first EV. We want to mitigate risk. Integration, we're building a new car from the ground up. We want systems to work in tandem. And performance, we work hard, we want to compete. We also took a quote from our mentor and friend and shop supervisor, Chris Vandelaar: "You don't have enough time to work fast," which ultimately means, you know, if you're rushing something, you're not doing it right the first time, it's going to take a lot longer because you're going to have to make it twice. So kind of moving forward from there, the vehicle dynamics is incredibly important to us. At Western Formula Racing, we like to kind of build the car from the ground up and start at a high level. So to do this, we really looked at like VD fundamentals and vehicle dynamics. We used a MATLAB simulation model that we created as students. And we also used data acquisition taken from testing. And on top of this, we took a simulator that we made as students as well. And this led to a minimized track width and a minimized wheelbase model. The tires we chose were 9-inch wide, 13 diameter Hoosiers, which we like to call the fatties. Yeah, so moving forward from there. The chassis, we have for the first time ever a full monocoque, which was done in a single cure cycle. And on top of that, we have an opening for the battery box, which is pretty awesome as well. And we have an integrated dash. We've also continued our development with carbon fiber reinforced polymer wheels. On aerodynamics, we make 40% more downforce, which we think is pretty awesome. We have our first ever under tray, and it's coupled with gurney flaps, which are pretty great. Yeah. We have an MRAX 228 motor, which is by itself, it's inverted by a Reinhardt drive, and then we have a Motec M150 drive. Controlling it, a custom-made control system. The gearbox was also custom-made by our students, which we're really proud of. It's a direct drive, and it has a custom housing, which allows for stiffness and ultimately like better serviceability. On the traction side, we made an effort to really focus on cooling to make sure that this vehicle works and it works well. So we used a simulation pulled from data from our simulator, pulled from data from our testing on the simulation model. And this used inputs that allowed us to cool the vehicle and ultimately create the model correctly. So we also used this model to size the battery pack. We sized it at 7.2 kilowatt hours, and we picked 665 cylindrical battery cells. As well, the case is made from carbon fiber reinforced polymer and glass fiber reinforced polymer. The reason for this was to keep it light and also keep it electrically insulated. We also focused on safety and serviceability using 8 different access hatches to really pull that off. It also features some late nights. It was Julian and I's capstone project. On the brake side, we have ductile iron rotors, and we have laser sintered pads, and we developed our braking and our design using MATLAB and a custom simulated program as well, driven from our initial simulator. The pedals, we use a carbon fiber reinforced polymer face, and we have a fully adjustable rack. On the suspension and steering side, we optimized our design for drivability and tunability, which is something that's really important to us as we go to 5 competitions, and it's something we want to be able to test. We also designed our package to stay within 10% of our peak aerodynamics, which is incredibly important. We also designed our anti-roll system to have 20% adjustability. And our dampers, hopefully this year, we'll be getting 4-post rig testing with our whole vehicle. On the steering side, we have a continuous fiber 3D printed wheel with a nylon matrix, something really cool. It's a single part. We were able to cut the weight in half with this. Our uprights are designed for high adjustability of steering quickness and Ackerman, so it's something we're planning on developing throughout the year. Lastly, on the ergonomic side, this is something that I think is really important, but from the ground up, we looked at using millispec data, a 5th percentile female and a 95th percentile male, and really designed the vehicle around those models. And something that I'm proud of there, and I can speak for the team, is that this is a vehicle that almost every person can fit in, which is awesome because we like to get our team members in the car and get everyone to drive it and experience this. So without further ado, I would like to hand things off to Alex for the component of the presentation I think a lot of people have been waiting for.
Thanks, Dean, for giving us a great behind-the-scenes look at what's been an absolutely monumental effort by the entire team throughout the last few months. Finally, I just want to recognize the extraordinary subsection leads, our senior team members, and all of our recruits that have worked tirelessly through long days and weekends and many sleepless nights to realize a goal that we as a team envisioned not all that long ago. On behalf of all the team leads, I just want to thank you for your passion, your dedication, and all your hard work. And now I think we've kept you waiting long enough. So the Western Formula Racing Team is proud to present, for the first time ever, the WFR 19E.